Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. What we're doing is mathematical modeling. Chapter 2 is discrete time models. Specifically, section 2.6 is now going to look at investigating equilibria and stability of higher order equations. Higher order gets complicated really fast, so we'll discuss order 2, which we've been doing in this course so far. This lecture specifically, what we're going to do is the definition and stability results for equilibriums of second order difference equations. Let's get to it. They're going to look like this, the non-homogeneous constant coefficient. Let's get to it. All right, definition for an autonomous second order difference equation of the form xt plus 1 is dependent on a function of xt and xt minus 1. We're going to focus on linear constant coefficient for the most part. We're not going to get too crazy. But that is just like we did before. It's a fixed point of the function f of, that should be f of xy if you had two coordinates, but really what we're saying is f of x star equals x star. You put x star in all of the coordinates, this one and this one and this one, and then you solve for x star. That's why we're going to do an example right away. So I have this homogeneous second order autonomous difference equation. What I'm going to do with that is find all equilibrium points of that, and it's going to turn out if and only if 0 is the only equilibrium point of these, always, for the homogeneous ones. For the non-homogeneous, if we have constant coefficient, we'll do that in a second. But what do we get from this? First of all, our f of xt minus 1 is equal to negative 3xt minus 2xt minus 1. If we were making that a function of x and y, like the analogy last time, this would be negative 3x minus 2y, the two coordinates. But what we're going to look for is we're going to let x and y both equal x star, and we're going to let xt plus 1 equal x star, and that's what we're looking for. So in this one, what we're going to get is x star equals negative 3x star minus 2x star. What I'm going to do is, how do I solve for x? I bring x star to one side, and then I isolate everybody else on the other side. What's going to happen here is if and only if we get x star plus 3x star plus 2x star equals 0. Factor x star out. This is if and only if 6x star equals 0. 6 can't be 0, so this says the only equilibrium for a homogeneous second order difference equation is going to be x star equals 0. And then what we're going to look at is the stability of, is 0 and stable equilibrium or an unstable equilibrium. We're going to get conditions for that. Let's do one more example where I add a non-homogeneous constant term into there, and those are the two main cases we're going to discuss the stability of today. Let's do that. All right, example 2 is going to look at a non-homogeneous case, but the only non-homogeneous part we're going to do is still just constant coefficient. So I've added a 12 to the equation from example 1. Find the equilibrium of this difference equation. It turns out there's only going to be one for linear constant coefficient, second order, or any order, in fact, because you're just going to put x star in all the terms. What are we going to get? Here we get x star minus or plus 3x star plus 2x star is going to equal 12 if and only if 6x star equals 12. And so this time we don't get 0, we actually get part of this deal, and we'll do this in general in a second, but right now what we get x star is 12 over 6, which is 2, which is actually the 12, the non-homogeneous m part, over 1 plus 2 plus 3, which was the p and the q that I'm going to use in the general form in a second. But in general, if you have an extra term there, this is always going to be what the equilibrium is every time. The number 2 for us. Now what do I do with that? We give you, from this, we see that if the moral of the story is going to be, if we have xt plus 1 equals f of xt minus 1, and it's homogeneous, linear, second order, then the only equilibrium is going to be x star equals 0. If we add that non-homogeneous term, so if we have, in general, what we're going to have is axt minus 1 plus bxt minus 2. That's always going to be the unique equilibrium, and we want to look at the stability of that guy. And if we have now xt plus 1 equals axt minus 1 plus bxt minus 2 plus a number m, the equilibrium is always going to look like m over negative a minus b plus 1. I'm going to turn those into positive p's and q's because we like everything to be positive, and grab the kitty because she wants to be in the video. So let's give, from example 1 and example 2, let's give the general form of the two linear constant coefficient second order difference equations we're going to discuss stability of today. All right, example 1 and example 2 are going to be just specific examples of these two cases that we're going to discuss in this video. In general, if we talk about non-homogeneous order 2, this is the way we presented it first, but for convenience, we're going to move these to the other side, and we're going to call P equal negative A and Q equal negative B, just so I can have some positive terms. And then we can see that if you put X star, X star, X star in there, the only way that works is the unique equilibrium will be X star equals 0. So for the homogeneous, the only equilibrium is X star equals 0. We want to know when that's stable or unstable. And oscillating, we'll get into it a little bit, but it gets complicated for even higher order. And then this guy is going to be the non-homogeneous guy that we presented. Normally was f of t, but we're going to make sure that that's just a constant number this time. And same thing, we're going to move these guys to the other side. And turns out when you put X star, X star, X star, you get 1 plus P plus Q. You factor it out, you divide, and the only equilibrium you get is this guy. Try it for yourself. But in general, we're going to get a theorem which says identical conditions. This one's stable if and only if this one is stable, and it'll be identical conditions. Let's get into that now. For the first case, stability of the equilibrium X star equals 0 for the homogeneous constant coefficient second order difference equation. What we're going to have is the characteristic polynomial is r squared plus pr plus q for convenience. That's why we made them p and q and moved them to this side. Suppose, regardless of how you make that characteristic polynomial, the steps are you get second order constant coefficient homogeneous, you find the characteristic polynomial, you find the two roots using the quadratic equation. When am I going to have to know how to complete the square? Yeah, to find the stability of this second order difference equation. What we're now going to do with those two roots is we know the general solution from previous videos is exactly this guy, C1R1 to the t plus C2R2 to the t. Therefore, to check the stability of this, and what stability means is we're looking for asymptotic stability if the limit as t approaches infinity of x of t is equal to 0 in this case, which is our equilibrium. That's what we're asking. That's what we mean by stability. Otherwise, it's going to be unstable. And so we know that we're going to have three cases. What are the three cases? Depending on the roots, if we have two distinct real roots, R1 not equal to R2. We could have case B is going to be one double real root. And the last case we'll gloss over a little bit, but it's going to be when we have the complex conjugates, when we have two complex conjugates. We're going to go through and systematically look at, there's going to be 6 cases here, there will be 2 cases here, and there will be 3 cases here. And when we look at all those different cases and when we have stable and unstable, we'll summarize this in one theorem and say if and only if the absolute value of these roots is less than 1, the maximum of them. Something like this. Let's go through all these 3 cases. All right, case 1, if we have 2 distinct real roots, first of all, what we're going to do, and you may have noticed I do it quite often anyways, in absolute value, if we have 2 real roots, I'm always going to call the one with the largest absolute value the dominant eigenvalue, and without loss of generality, we're going to let R1 be the biggest one in absolute value. Then what that means is if I divide R2 by R1, because R1 was larger, this guy is less than 1. And so what we're going to say is this limit of this term is going to go to 0, we notice. Therefore, if I cleverly factor R1 of t out of both terms, then I get this expression, and the end behavior of our solution, which we have an explicit form for in this case because it's homogeneous second order, is completely determined by that the end behavior of the dominant root of the characteristic polynomial. So now we have 6 cases dependent on whether r is larger than 1, equal to 1, between 0 and 1, between -1 and 0, equal to -1, or less than -1. We're going to go through all cases and see in the pictures whether we get stability. Then we're going to go to case 2, which is case B, whether we have a double real root. Then we're going to do case C, which is complex conjugates. For now, let's do the 6 scenarios we get with 2 distinct real roots. If R1 is larger than 1, then the limit as x approaches, as t approaches infinity of xt is going to equal positive infinity. This leading term is going to get larger and larger. Think of 2, it'll just keep growing and growing and growing, and that's exactly what happens regardless of our initial condition. You're just going to get that it grows. In case 2, if we have that r is exactly equal to 1, then what that's going to say is we're going to get a constant terms, the limit as t approaches infinity of xt is going to be our starting point, and we're just going to get a constant solution, which technically is stable, but not asymptotically stable, which will be the theorem we want. In case 3, now we're going to do if r is positive but less than 1, that's going to be the good one. That's going to be asymptotic stability. That's going to say that the limit as t approaches infinity of c1 r1 to the t is going to be, and therefore our solution is going to be 0, and that, remember, is our equilibrium. So in that picture, what's going to happen is we will start somewhere here, and then it is going to have to be asymptotically stable towards our equilibrium 0. If we now go to the negative half of the real number line, now what we're going to have is if we have negative 1 is less than r1 is less than 0, what we're still going to get is, oh, now we need, you can already see what's going to happen. It's going to oscillate about our equilibrium, so I need the other half of the plane. So this is still going to go, the limit as t approaches infinity of r c1 r1 to the t is still going to equal 0, but it's going to oscillate about 0. We're also interested in whether it's oscillatory or non-oscillatory, so the theorem is going to have 2 conditions: when it's asymptotically stable, and if and only if when it's oscillatory. And it's oscillatory if and only if it has no real roots which are larger than 1. We'll state the theorem in a second. I don't think I said that right. Yeah. 5. What's our picture for that one? For this one, it's still going to converge to 0, but it's going to flip back and forth. So if we have here, then it's going to go like this, and it's going to get smaller and smaller and closer, but it will converge to 0, but in an oscillatory fashion. This one is not flipping back and forth, but they're both converging to 0. In number 5, what we have is if r1 is exactly equal to negative 1, then we're going to oscillate between c1 and negative c1, those two guys. And what's going to happen there is we will just have a constant wherever we started. It will just end up going c1, negative c1, c1, negative c1, and we'll just get flipped back and forth to 2 values. And in the last scenario, if r1 is strictly less than negative 1, what we're going to get is that it's going to grow to infinity, but it's going to oscillate in between values. Think about negative 2. Negative 2 squared is 4. But then negative q cubed is negative 8, and then 16, and then negative 32, and it's going to get bigger and bigger, but flip back and forth on the either side of 0. So this is going to get increase to infinity, or get larger and larger, but oscillate about 0 still. So what that's going to look like is, regardless of where I start, it will do this, and get larger, and get larger, and get larger, and I run out of board space, but it's going to get larger and larger and be oscillatory. So this is the category and the scenario of what the overall theorem, and when we pull this all together, is going to try and say. More importantly is it's going to be asymptotically stable if and only if these 2 cases, if your absolute value is less than 1. And then they're going to have an oscillatory statement. Oscillatory if you don't have any real solutions, positive. All right, let's do the next case, case B. All right, case B, if we have a double real root now, r1 equals r2 equals r for simplicity. We don't need an index this time, so I won't use it. We know the general solution to find the 2 linearly independent solutions for this is going to be c1 plus c2t times r to the t. And then what we do is we're going to factor that back in and cleverly split we want to know what the end behavior of this guy is. I can split it into 2 terms. This one already, so now let's do case 1. If the absolute value of r is less than 1, which means that r is between negative 1 and 1, we know that the limit of this guy is going to be 0. And why is that? Well, this limit, if r is less than 1, this one is definitely going to go to 0. So that term is 0, and this one we claim is also 0. Why is that? It's L'Hopital's rule. T is going to infinity, so is t, I would hope. And then because r is less than 1, this is going to 0. So what this actually is 0 times infinity type. And then what I would do is divide by, or write this as 1 over r to the t, take the derivatives, and then you can see that this actually goes to 0. So this will actually go to our equilibrium 0, which means, long story short, in this second case B, when we have a double real root, again, if the modulus is between negative 1 and 1, we have asymptotic stability. If we have that the absolute value of r is larger than 1, then we're going to get diverges. If we have that r is greater than or equal to 1, then we're going to get that it just grows monotonically, and we're going to get that it grows in an oscillatory fashion if that r is less than -1. And then therefore that means, long story short, unstable in this condition. We're trying to get a global theorem for when we have stability of 0 based on the roots of the characteristic polynomial. Let's do the last case, case C, where we have two complex conjugates. All right, case C is when we have two complex conjugates. I know depending on the background, you may not have seen a lot of complex variables, and this is the general solution I gave in our notation for completeness in the previous videos, but I'm going to make one more move where you can combine this using a clever substitution. Here's the clever substitution, but essentially why I want to do this is I don't want to have a cosine sine term. I just want to be able to write the general solution as one term of our exponential grow guy and then this oscillatory thing. In all three cases, what this is going to say is because I have an exponential part which is growing, this is a real number and it's going to grow when I put t in there larger and larger. But here, regardless of what the t is, that's going to oscillate, and this is often how we describe heat and wave equations and all these things. It's going to, the heat of the element is going to decay over time, but it's going to oscillate in an oscillatory, in a wave type fashion. So we know that because the cos t is there, as soon as you have complex conjugates, we know that all the solutions are going to be oscillatory. And then depending on this guy, we want to know whether it's going to grow, stay constant, or decrease. And so let's get to it. If k is larger than 1, we're going to get oscillatory. That means that pictorially, if you're in now the complex plane, that means that those two roots are outside of the unit circle. And if that happens, like, you need to know that, but if that does happen, then we're going to get oscillatory but increasing. Because this will stay oscillating, but this is now going to grow, so the points are going to get bigger and bigger as we go. Unstable is the moral. If k equals 1, again, we're going to get oscillatory, but with constant magnitude. It's just going to flip them back and forth between two values, which is technically stable, but not asymptotically stable. It's not converging to the equilibrium still, but this is technically stable. But what we're looking for is asymptotic stability, which is the last case. If we have that k is less than 1, then these guys are actually inside the unit disk now, and that will say that the limit of this will in fact crush to 0, and if you have a limit of something is 0 and the other one is bounded, then or this one's 0 and the other one is bounded, the limit of the overall is 0, so this limit will be 0 and it's going to converge to 0 in an oscillatory fashion. This is all three cases, and all the cases dependent on those roots. Now you can see we had to draw a whole bunch of diagrams. I got lazy in case B and we didn't draw these. But the first theorem that we're going to do now is going to encapsulate this. One of the statements is going to talk about asymptotic stability and when that happens, and we're going to have an if and only if necessary and sufficient conditions. And then the second statement, which you can pay a little bit less attention to, is they're trying to describe when it oscillates and when it doesn't oscillate about that equilibrium. The good news is the behavior is the same when we put that constant non-homogeneous term in there. Let's state the theorem. Theorem A. If we have for the unique equilibrium x star equals 0 for the difference equation, which is homogeneous second order constant coefficient, and if we already know explicitly that this is the characteristic polynomial, what we're saying here is the two conditions. This is the one you want mostly, but this is the oscillatory condition. Condition 1 says that the unique equilibrium 0 in this case is asymptotically stable if and only if the maximum modulus of those two roots of the characteristic polynomial, if both of them are less than 1. So if you get 1/2 and -1/3 of your roots, the absolute value of those is 1/2 and 1/3, and they're both less than 1, and therefore automatically asymptotically stable. I don't have to do anything else. Good condition. And then the other condition is telling us when this oscillates, our solutions xt oscillate about the equilibrium x star equals 0 if and only if our characteristic polynomial has no real positive roots. That seems strange, but this is an extremely useful condition. Check that it has no real positive roots, it oscillates. If both of the moduli are less than 1, it's also asymptotically stable. Let's do the analog to the non-homogeneous case where we put a real number m there instead of 0. Okay, to finish off, we're going to do the non-homogeneous case where m is a real number. And so for this second order difference equation, we're going to have that the unique equilibrium is x star is m over 1 plus p plus q. And here we're going to notice that x star is a particular solution to this difference equation. And so we know that the general solution is the homogeneous part plus a particular part. And in particular, this time what we're going to have is the homogeneous part, which we just did last time, plus this equilibrium, x star. And therefore what we notice, and then we can quickly state this, an analogous theorem for this equation, that means that the limit of xt, our solutions, will approach our non-zero equilibrium for the non-homogeneous system if and only if the homogeneous part for the homogeneous difference equation attends to the unique equilibrium x star equals 0. And similarly, xt, our solutions, oscillate about the non-zero equilibrium if and only if the homogeneous solutions oscillate about the equilibrium 0. Therefore, we can state an analogous theorem for the asymptotic stability of the equilibrium x star equals m over 1 plus p plus q, just like we did for x star equals 0 for the homogeneous case. Let's do that. To finish off, Theorem B is going to say for the unique equilibrium x star, which is m over 1 plus p plus q of this equation, which is the non-homogeneous case, constant coefficients, and having the characteristic polynomial r squared plus PR plus Q, which has roots R1 and R2. What we have is asymptotic stability if and only if the maximum modulus of these guys is less than 1. And we have that the solutions oscillate about x star if and only if the polynomial P of R has no positive real roots. Exactly analogous to Theorem A, except now for the non-homogeneous case. Let's do a couple examples and then we're done. All right, example 1, we'll do a homogeneous example. And so we know if it's homogeneous, immediately we know the unique equilibrium is x star equals 0. And then I want to classify the stability of this. And how do we do that? I find the characteristic polynomial, I find the two roots, and then we analyze using the theorem. So what is our characteristic polynomial? P of R is going to be r squared minus 5 over 6r plus 1 over 6. And I want to know when does that equal 0. Cleverly, I've already done this because I cooked them up, but this is if and only if what adds to give me negative 5 over 6 and multiplies to give me 1/6, negative 1/2 and negative 1/3. That's correct. So we can factor this as P of R is going to be r minus 1/2 and r minus 1/3 equals 0. So that says our two roots are r1 is 1/2 and r2 is 1/3. And this is what I always try to do. I've made r1 the dominant eigenvalue anyways, but let's see what that says. Therefore, because they're both real and positive, that immediately says, first of all, let's do the asymptotic stability. Let's do it in the order that the theorem says. So for the condition 1, is this asymptotically stable? We want to look at what is the absolute value of R1. That's the absolute value of 1/2, which equals 1/2. And the absolute value of R2 is the absolute value of 1/3, which is 1/3, which is implies that the maximum of the modulus of R1 and R2 in absolute value is equal to the maximum, now you can see, of 1/2 and 1/3. 1/2 is the biggest number, so we pick 1/2, which says that 1/2 is less than 1, so we get asymptotic stability of 0. So that says x star equals 0 is asymptotically stable by Theorem A, part 1. Now for oscillatory, it's not oscillatory because it oscillates if and only if it has no real roots of the characteristic equation. This one has two real roots, and therefore by Theorem A, part 2, we know that this is not oscillating and asymptotically stable. Let's do one more where we have complex roots. Okay, for another one we have homogeneous again. We'll do an example 3. I forgot we didn't do a non-homogeneous one, so example 3 will be last. Not done until you're done, until I say you're done. So this time we have homogeneous again. I know that the unique equilibrium is 0, and we want to know the asymptotic stability of this, and then we want to know whether solutions oscillate about 0. So for asymptotic stability, or both of them, either way, I need the characteristic polynomial and their roots. The characteristic polynomial this time is P of R equals r squared minus 2r plus 2. When does that equal 0? I'm going to steal one of the ones. This is only if r squared minus 2r plus 1 is equal to 0. And then I already see, if you know what you're doing, this is complex because when I move him to the other side, he's -1, so we're going to get the square root of -1, which is I. Anyways, this says we have r minus 1 squared plus 1 equals 0 if and only if r1 and 2 are equal to 1 plus or minus the square root of -1, or r1 is 1 plus I and r2 is 1 minus I. We did this one as a homogeneous scenario for in the video where we did solutions to homogeneous equations. You can go back and look at that video. But now we're trying to talk about the stability of 0 in this scenario. First of all, we know that because we got complex, we're going to have these cosine and sine functions, so we definitely know we don't have any real roots which are positive, so we know it's oscillatory for sure. But first of all, do we have stability? No, we don't, because if I think about the modulus of complex numbers, this is going to be square root of 1 plus 1, which is root of 2, which is larger than 1 for both of them. Therefore, these ones are going to be not asymptotically stable. They're going to be unstable and oscillating and growing as we go. Let's see what that means. So these are my two roots. Even without those, I'm just going to check their maximum moduli. What this says for a complex number, the modulus is actually the square root of alpha squared plus beta squared, which is in this case 1 squared plus 1 squared, which is root 2. And for its conjugate, it's the same. They're both on the same circle, on antipodes of each other. This is going to be the square root of 1 squared plus negative 1 squared, which is still the square root of 2, which is larger than 1, which is larger than 1. And so that this says the maximum of the modulus of R1 and R2 is equal to the same thing, which is root 2, which is larger than 1, therefore if and only if unstable. If it exactly equals 1, you got to be careful because technically it might be stable, but it's definitely not asymptotically stable. If it's larger than 1, you can say unstable. And this is again from Theorem A, I called it, part 1. And then for part 2, we automatically know that our solutions are xt or c1 root 2 to the t and cos, what was it going to be? I think pi over 4 we cheated to t, and then plus c2 root 2 to the t sine pi over 4t. So this is going to be our general solution once I have this. And remember, the pi over 4, we need the polar form, so we need to write our two solutions, R1, 2, or at least one of them as our modulus R, or I think I called it k in the last time, times e to the pi over 4. And so we find our k is root 2, and then pi over 4 I is what I'm trying to get at. Once we have that as our roots in this polar form, not the Cartesian form, then we can get this explicit solution. I'll spare you, but you can cleverly write this as just a cos form. But either way, we see that the root 2 is larger than 1, the k is larger than 1, so we get oscillatory. It's growing, so it's unstable, and it's definitely oscillatory by Theorem A, part 2. This is definitely xt oscillates about x star equals 0 was the long story of what I was trying to spit out there. So Theorem A, part 1 tells us it's unstable because the maximum modulus was larger than 1, and because our general solution is two complex conjugates, we have no real positive roots is the point, and therefore it oscillates about 0. Let's do one more non-homogeneous. That was 3. Oh, that was 3 also. 720. What is it in radians? All right, to finish off, we'll do a non-homogeneous case. We have this non-homogeneous constant coefficient second order difference equation. What we're going to do with this is first find the equilibrium. We already know what it is, but I'll do it again. What we're doing is x star plus 3x star plus 2x star equals 12, or this is the p and the q. So the unique equilibrium x star is m over 1 plus p plus q. In our case, m is 12 over 1 plus 2 plus 3. 6 is perfect. This is the sum of its proper divisors and the product of its proper divisors, which means, long story short, this is 6 over 12, which is 2. Our unique equilibrium this time is non-zero and equal to 2. We want to know if this is stable or unstable. It turns out it's going to be unstable and oscillatory about 2, our solutions. Why? From Theorem B now, what we see is we have to factor our characteristic polynomial is r squared plus 3r plus 2 equals 0. When does that happen? That's going to be r plus 1 and r plus 2 equals 0. So that's going to say that r1 is negative 2 and r2. I've made it the dominant one in absolute value again, is what we always do classically. And then what I'm going to do with this is, first of all, is it asymptotically stable? No. We know that the absolute value of r1 is going to be the absolute value of negative 2, which is 2, which is larger than 1, and the other one's smaller. But this is the absolute value of r2 is going to be the absolute value of negative 1, which is 1. But what does that tell us? The maximum of the absolute value of r1 and r2 is equal to 2 in this case, which is larger than 1, so unstable. And from condition 2 of Theorem B, we see that we have their two roots are negative, so we have no positive real roots to our characteristic equation, which says if and only if oscillatory. This says that since R1 and R2 are both less than 0, we have, by Theorem B part 2, this tells us that our solutions oscillate about x star equals 2, and it's unstable, so it's going to grow away from it, but oscillate around x star equals 2. Please subscribe right here, hit the notification bell. I'll see you next time.